This is 2020 European Girls Math Olympiad problem number 6, and here is a view of this what is this problem? Algebra problem, I guess, of this algebra problem. Well, it has a lot of algebraic manipulations, but relatively straightforward manipulations. So here is the question. Let m be greater than 1, be an integer, and a sequence is defined recursively such that the initial 3 terms are this, and for any term greater than or equal to 4, here is the recursion. Here in this recursion, something annoying is we don't know the value of m, and that's exactly what the question says. If you want all the terms of this sequence, a1, a2, a3, so far the first 3 terms are all squares. For what values of m would all the terms in this sequence will end up being squares? All right. And yeah, so that's pretty much it. So let's go ahead and I think noticing that there's nothing, I mean, until we have a better idea, we might as well just randomly start substituting some values for m to see what type of values come out correctly, and then maybe from there we can have an interesting observation. So if m were 2, then the recursion will end up being an is equal to, well, 2 times an minus 1 plus a sub n minus 2 minus a sub n minus 3. And now, because we are given the initial conditions, we might as well just go ahead and try to calculate a4, a5, and so on. So if you were to calculate a4, that would be 2 times a3 is a 4, so 4 plus a2 is a 1, and then a1 is another 1. And interestingly enough, 5 times 2, 10 minus 1, that's a 9, and indeed that's a square. Aha, check. m equals 2 is promising. Let's check a5. It's 2 times the previous term, which is a 9, plus 2 terms before, that's a 4, minus 1 again. 13 times 2, 26, minus 1 is 25. Again a square. Oh my goodness, that might work actually. a6 is 2 times. Okay, let's convince ourselves one more time. 25, the previous term, the one before that, minus the one before all that, which is a 4. 25 plus 9. 34 times 2, 68, minus 4, 64, and indeed that's a square as well. Now that I realize it's a square, I want to go a little bit further to see if there's any pattern, which I think you guys have already seen the pattern, right? a1 and a2, they are both 1 square, a3 is 2 square, and now the sequence continues as 3 square, 5 square, 8 square. I think it's clear from here that when m is equal to 2, it seems, at least, we can use induction to prove this, but it seems like this is just f sub n squared or shifted. But it's the Fibonacci sequence squared, right? Well, we need to prove this using induction or some other stuff, but for the time being, okay, let me skip that case. This case seemed to work. Let's make a note, seem to work. All right, so let's go to m equals 3. I mean, immediately you can see that m equals 3 will not work. For instance, a4 is equal to 3 times 4 plus 1 minus 1. And check what? 5 times 3 is 15, minus 1, that's a 14, and again, not a square. So this failed. If we try m equals 4, a4 would end up being 4 times 4 plus 1 minus 1. 5 times 4, 20, minus 1, 19, again wouldn't work. You can keep going, but I think you guys can see where the next m that will end up working, right? So a5 is equal to, because each time, sorry, not a5, a4 again. a4 is equal to 5 times m is 5. 4 plus 1, this is always a 5. 5 times a number, an integer, minus 1. So we are talking about integers on its units digit ends up with either a 4 or a 9, and we want this to be a square. So this attempt will give us 24, right? 5 times 5 is 25, minus 1 is a 24. Again, fail. So what is the next square which ends with a 4 or a 9? So 29 won't work, so we might as well skip m equals 6. yeah, that won't work because a4 here will come out as, I mean, you can just plug it in, so this 29 won't work. M equals 7 will come out as, well, if you plug in m equals 7, a4 comes out as 34. Again, not gonna work. You guys can see 39 not gonna work, 44 not gonna work, but 49 has the potential of working it, and m equals 8 won't work. Why? Because a4 here will end up being 39, not work. Let me just write it. Well, okay, let's just keep writing on that sequence. M equals 9, a4 will come out as 44, not gonna work. But finally, when you try, let's write it on this space here, m equals 10. Again, this has the potential to work because a4, when you plug into the recursion, it is 10 times 4 plus 1 minus 1, and indeed 5 times 10, 50 minus 1, that's a 49, which is 7 square. But like in the previous case when it actually worked, m equals 2, I want to really see if I can figure out a pattern so that it can give me a guess. So I might as well continue calculation. So a5 would end up being 10 times 49, I should say. 49 plus 4 minus 1. 49 plus 4 is 53 times 10, 530 minus 1, 529. And if you remember from your number sense days, that would be 23 square. A6, you can try, okay, let me do one more. So that would be 529 plus 49 minus 4, I think. There you go. So 529 plus 49 is 578 times 10 is 5780. Subtract 4, 5776. And this one, I won't lie to you, I did use actually a calculator. That gives me 76 square. And so on. Now, as you can see here, the pattern is slightly harder to see. Okay, so let me rewrite so far what we have. A1 is 1 square. A2 is given in the problem, it's also 1 square, and finally A3 is 4, which is 2 square. So what is the pattern that generates 1 square, 1 square, 2 square, 7 square, 23 square, 76 square, and so on? Yeah, so you need to either guess that pattern, just like we did in the previous case, and then find a closed form formula using induction or some stuff. But guessing here is slightly harder. Technically, the guessing is extremely simple if you use the characteristic polynomial of this difference equation, in a sense, right? So, but I don't want to go into that. If you check it on AOPS, actually one of the users which I'm using the solution today is A1267. So he has in detail how you guys can calculate the characteristic polynomial. If you've taken a linear algebra course or a differential equations course, you would know exactly how to do that. So, but if you haven't taken those advanced courses previously, you should be still able to guess it, but it's yeah, so it's a little bit more challenging to guess what is the recursion which will generate all these numbers. In the previous case, it was easy, right? 1 square, 1 square, 2 square, 3 square, 5 square, 8 square. This is obviously the Fibonacci squares. All right, so, but then I don't want to keep going like this. I know already that m equals 11 will definitely fail because a4 will come out as 49, 54. 54 is not a square. M equals 12 will give me a4. Which will end up being 59, won't work. M equals 13, that one is promising. A4 will come out as 64. However, when you calculate A5, that will be 13 times 64 plus 4 minus 1. And that thing will come out as not nice. I think 883, which is not a square. So failure again. Yeah, so at that point, you might think that maybe it's not gonna work for anything else except that m equals 2 or m equals 10, right? So we need to first prove that that's the case. There's no other candidates. And then once we establish there's no other candidates other than 2 and 10, then we need to verify that this is true, and then verify a recursion for m equals 10 as well, and then we would be done. Well, let's quickly check. The whole solution is based on a very cool trick that I'm sure if you've done AME in the US previously, you would have seen this trick before. And it is the following trick. So we are already given, let me just rewrite what the given so far. A1 is 1 square, which happens to be also A2. And A3 is 4, which is 2 square. Now A4 was given to us as m times, where m is an integer, positive integer greater than 1, A3 plus A2 minus A1, and so on. Recursively, we will keep writing it down. Yeah, A4 is given as such, and now what I can do is I can plug in the values for A3 and A2 in this formula. Let's quickly do that. So this is just m times A3 is a 4, plus A2 is a 1, minus A1 is a 1. So that's just 5m minus 1. Similarly, if I keep going a few more terms, m times A4 plus A3 minus A2, so that's the valuation for A5, which is A4, which is a 5m minus 1, and A3 was just a 4 minus 4, sorry, plus 4 I should say, minus 1, and that's simply 5m squared plus 3m minus 1. And now I will just go ahead and do it one more time for A6 as well, and then from there we will get to the desired result. M times, okay, A5 plus A4. A5 was this monster over there, let's just write it out. Minus 1 plus A4, which is this monster over here, 5m minus 1. All subtract from this 4. Now, if you bash through the algebra, which we can do it quickly, so we have 5m cubed, clearly 5m cubed. We have plus 3m plus 5m, so plus 8m squared. After we multiply, this is minus 1 here, minus 1, so that would be a minus 2m. And then we still have a minus 4 outside. Alright, so this is A6. Now the trick, which is out of the blue, I think during the actual exam, maybe I wouldn't have seen this. Most likely I wouldn't have, well, I don't know, maybe if I looked at the same problem for a whole hour, maybe I could have seen that trick. But the trick is the following. Because we want an m that will make each of these expressions a perfect square, right? We want each of these expressions to end up a perfect square. Check this out. A4 is a perfect square. And I'm going to skip A5. I will also check with A6 now. So A4 is a perfect square. A6 is a perfect square. Their product is a perfect square. In fact, I will multiply their product also with a 4. That also is a perfect square. Aha. So now, check this out. Well, I can see your frustrations, but once I show you the trick, you will kind of guess where this thing came from, right? So let's plug in these values. So basically, we are saying that 4 times A4 is just 5m minus 1. A6 is that monster, 5m cubed plus 8m squared minus 2m minus 4. And indeed, if you expand it out, yeah, so don't be lazy, do it. 100m to the 4 plus 140m cubed minus 72m squared. I hope I didn't mess up my calculations here. Minus 72m plus 16. So that's what comes out. And this expression is supposed to be a perfect square. Perfect square, right? Now, check this out. So let me just make it slightly smaller. Okay, good. What I will do is I will try to look at the closest square to this thing. Well, obviously, because the leading, so this is a 4th degree polynomial, and the leading coefficient is 100. So my the square that I'm considering is the following: 10m squared. And then because there's a 140 here, trial and error, you would see that this would be a 7m. And now I will consider the following 2 expressions. So first I would like to calculate this one. Very straightforward, just square it. If you square it, you'll get this: 100m to the 4 plus 149m cubed, I think, cubed, minus 91m squared minus 98m and plus 49. Now I want you to compare this expression that we found earlier, this one, and this new expression. Which of these two expressions is larger? Now when you check that, compare the first m to the 4 terms. These are the same. These two expressions, well, when I compare them, well, apparently, wait, this is not 149, sorry for that. This is 140 as well. When you just square this expression, this comes out as 140, my bad. So these two terms are also the same. Actually, let me use the same color here. So those two terms are the same. I'm just comparing the expressions, right? These two are the same. Now the remaining terms are the ones that we need to compare. And so if you compare these remaining terms, you can either construct an inequality and find the direction, but I think this one is pretty clear, right? So comparing these two expressions, the square, this is minus, but this one is further minus. This one is definitely smaller, right? So this one is smaller. And besides, when you compare this one, minus 98m versus minus 72m, remember, m is greater than, strictly greater than 1 is given in the problem. So again, the second one is smaller. Now, when you compare the last two terms, then this one is the smaller one. But obviously, because m is greater than 1 or greater than or equal to 2, clearly, the gain here is, this one is larger than the second one by more than 20, like almost 20, 19. And here, this one is larger than that one by 26. And the gain is only 33, right? Or if you don't like this, just write it out as an inequality, right? So it's very simple. But so then necessarily, this guy is larger than, so this monster is larger than this monster. Do you guys see that? So this implies that 4 times a4 I should say, a4, a6 is greater than 10m squared plus 7m minus 7 all squared. Now there's another expression that I want to look into, and it is this one, 10m squared plus 7m minus 6 squared. And when you expand this one out, you find something like this. In the end, 100. It will start out the same way, obviously, but then the ending will be slightly different. Minus 71m squared minus 84m plus 36. Now, when you compare again this term, this with that one, again the first two terms are the same. So let me just highlight them. That one and that one are the same, obviously. And then besides, the second terms are also the same. All I now need to finish is to compare these two terms, those two terms, and these two terms, right? Because these terms are so close to each other, let me go ahead and this time use appropriate inequalities. But my claim will be the following. I claim that this time that one is greater than this one. All right. So my claim is that 10m squared plus 7m minus 6 all squared exceeds 4 times a4, a6. Well, I just plug in these expressions, polynomials in m, but I already know that there are some cancellations, namely those two will cancel and these two will cancel. So what will be left as a result will be the following. For this one, we have this minus 71m squared minus 84m plus 36 is greater than, on the right hand side, we were just left with minus 72m squared minus 72m plus 16. Now move things onto the same side. For instance, move all these onto the left hand side, even this one, everything into the left hand side. So we end up with m squared. So this implies m squared minus 12m, and then 36 minus 16 is plus 20 is greater than 0. And then that gives me the condition for m for that to work. M minus 2 times m minus 10 is greater than 0. And from your functional analysis, you will notice that because m is strictly greater than 1, so this is just a parabola with two roots, right? A root at 2 and then another root at 10. and this parabola will be greater than 0 only if m is less than 2, which it can't be, right? Because m, by definition, it's given in the problem statement that m is strictly greater than 1, or m is greater than 10. So therefore the part which is binding is this side. So m is greater than 10. So as long as m is greater than 10, we have this expression is, well, okay, here. This expression is strictly greater than that. But then, wait a second. Earlier we found that 4a4a6 is greater than this thing. Now we're saying that 4a4a6 is less than this new expression. So we can squeeze 4a4a6 between these two squares. But more importantly, those two squares, they're what? Consecutive squares. And obviously you won't be able to find a perfect square between two consecutive squares, right? Aha! So therefore this implies 7m minus 6. So this one holds when m is greater than 10, right? So therefore what it does is, obviously this is impossible to squeeze, an integer, especially a square, right? A square between two consecutive squares. Do you guys see that these two are consecutive, right? So they are just one apart from each other. And because you cannot fit another perfect square between two consecutive squares, this cannot be true for m is greater than 10. But we early on, at the very beginning of the problems, when I tested out cases, I already ruled out m equals 3, 4, 5, 6, 7, 8, 9 were gone. And now I'm saying that anything larger than 10 is also gone. So all that is left is just to verify that m equals 2 works and m equals 10 also works. These two cases also work. For m equals 2, I already have a guess. an is equal to fn squared. For the second one, I don't have a guess, but well, I'll just make the guess. Don't worry about it. Well, the guess is a little bit harder to see. Well, okay, so let's just go ahead and do that. So therefore, we are given, just to summarize, we are given a1, a2 equals 1, a3 equals 4, and then this recursion an. Let's start with the case m is equal to 2, right? M is equal to 2. All we need is to verify that indeed this works. 2 times a sub n minus 1 plus a sub n minus 2 minus a sub n minus 3. And our claim is that a sub n is just equal to f sub n squared, where f is the Fibonacci sequence, right? F sub n squared, where f sub 1 is equal to f sub 2, which is equal to 1, and f sub n is equal to f sub n minus 1 plus f sub n minus 2. So I want to show you that if there is such a sequence an which satisfies this recursive relation as well as these initial conditions, then necessarily that sequence an better be the Fibonacci numbers squared. And a very cool trick is the following. If I were to replace each of these by the corresponding f sub n minus 1, f sub n minus 2, and f sub n minus 3, each squared, then see if this comes out as f sub n squared. If it does, then we are done. It confirms the validity of the claim. And indeed, so let's start with 2 times f sub n minus 1 squared, because that's what we claim a sub n is, plus f sub n minus 2 squared, and subtract from it f sub n minus 3 squared. Well, the trick is the following. This thing turns out to be exactly equal to the following expression, f sub n plus, and then minus later on, plus n minus 2 squared plus f sub n minus 1 minus f sub n minus 2 squared, minus, I think we still need to make another adjustment here, f sub n minus 3 squared. Well, I didn't change the last term, it's still there, but you guys need to confirm that this when you add up these two expressions, it gives me exactly this one, which makes sense, right? Because f sub n minus 1 square here, f sub n minus 1 square here, 2f sub n minus 1 square, that makes sense. And then similarly, we'll get 2f sub n minus 2 square. But then the 2 times f sub n minus 1, f sub n minus 2 here, a positive sign, the same expression with a negative sign here, so done, right? So this is correct so far. But wait, the definition of f sub n is such that it's equal to this. I can replace this sum here with f sub n squared plus this one can be also that one is f sub n squared. How about this difference squared? Yes, that one would be f sub n minus 3 squared, right? Do you guys agree? Because f sub n minus 3 f sub n minus 3 only inside, but then we have a square from this one. Yeah, so because f sub n minus 3 plus f sub n minus 2 will give you f sub n minus 1, and so yeah, that's good. And then minus f sub n minus 3 squared. Hey, these two terms cancel. Oh my goodness, we found exactly what we needed. So f sub n satisfies this recursive relationship. Now we need to also verify the case m is equal to 10, namely again that we have sequence a1, a2, initial conditions 1, a3 is a 4, an is given this time as 10 times a sub n minus 1 plus a sub n minus 2, subtract from it a sub n minus 3, and okay, so long behold, the claim is the following. After you work out those initial values that we calculated somewhere up there here, yeah, so it's hard to see. So 1 square, 1 square, 2 square, 7 square, 23 square, 76 square, unless you know the characteristic polynomial and how to deal with those. Then the claim is the following. I claim that a sub n is the square of this other sequence, recursive sequence b sub n, and the square of b sub n, and where b sub n is given by the following initial conditions, where b sub n is simply equal to, well, okay, let me first write down the initial conditions. B sub 1 is minus 1, b sub 2 is a 1, and the recursion is b sub n is equal to 3b sub n minus 1 plus b sub n minus 2, I believe. That's it. So all we need is to verify that when I substitute here for a sub n minus 1, a sub n minus 2, and a sub n minus 3 expressions, corresponding expressions for b sub n squares, then we need to check that this should add up to b sub n squared. Let's go ahead and do that. So we have a n is equal to 10 times, replace a sub n minus 1 with b sub n minus 1 squared, plus, and then the same thing on the next one. The next one would be b sub n minus 2 square minus b sub n minus 3 square. And now the trick is pretty much along the same lines that we did earlier. If you work this out, you will see that this is just 3b sub n minus 1 plus b sub n minus 2 squared plus b sub n minus 1 minus 3b sub n minus 2 squared, and I still need that b sub n minus 3 square term. Let's quickly check that. So we have 9b sub n minus 1 squared plus 1 more b sub n minus 1, we will get 10b sub n minus 1 squares. Similarly, we will get 10b sub n minus 2 squares, and then the cross term 3b sub n minus 1, sorry, 2 times. So 6b sub n minus 1, b sub n minus 2 here, another 6b sub n minus 1, b sub n minus 2, except their signs are opposite, so perfect, they cancel each other, and so those two expressions are the same. But then, looking inside, I can replace this term here with what I see from this recursion. It is just b sub n square plus, how about this one? Again, looking at this recursion, oops, there's an invisible 2 here. Looking at that, I see that this is just b sub n minus 3 there, right? So b sub n minus 3 square minus b sub n minus 3 square. Aha, those two cancel, and again, I'm left with b sub n minus b sub n squared, which is equal to a sub n, and that proves the validity of this claim that indeed So going back to our original problem, this recursive equation will yield perfect squares. Each of the terms in this sequence defined as such recursively will end up being perfect squares only when m is equal to 2 or 10, as we have proven it. Thank you.